All right, let's talk about something that's absolutely crucial if you're making that jump from data science to AI engineering. We're going to break down how a few key software design patterns can take your projects from, experimental notebooks to solid production-ready MLOps systems. So let's kick things off by framing a problem that I'm betting pretty much all of you have run into as your projects start to get bigger and, well, a lot more complicated. So does this hit close to home? You know that feeling, right? As a data scientist, you've definitely hit that wall where the code that was beautiful and worked perfectly in your notebook suddenly feels like it's made of glass the second you try to get it into production. It's just brittle. And yeah, these are the classic growing pains. It feels like your code is fighting you at every turn. Want to add a new model? Get ready for a massive rewrite. System configs? Oh, they're buried somewhere deep in the code. Good luck finding them. And debugging? It's turned into this absolute nightmare. If any of that sounds familiar, hey, you are not alone. This is the classic sign that it's time to shift your thinking. A little less like a scientist and a little more like an engineer. So what's the fix? Well, it's a concept that software engineers have been using for decades. It's their secret weapon, really. We're talking about design patterns. Okay, so what in the world is a software design pattern? Think of it like a recipe. It's a proven, well-tested way to solve a common problem. It's not the finished cake, right? It's the step-by-step guide, the blueprint that tells you how to mix the ingredients. You're basically leveraging solutions that other developers have figured out over years and years. And this is exactly why these patterns are a game changer for MLOps. They go right after those growing pains we just talked about. They give you flexibility, so you can swap out models or frameworks without a headache. They force you to write better, more structured code, which means it's way more stable and easier to maintain. And maybe best of all, they stop you from reinventing the wheel, so you can focus your brainpower on the actually interesting parts of your project. All right, let's get practical. We're going to build out your MLOps pattern toolkit, starting with 3 of the most powerful patterns you can start using, like today. First up, we've got the strategy pattern. And trust me, this one is a cornerstone for MLOps. The big idea here is to define a whole family of algorithms, wrap each one up in its own little package, and then make them totally swappable. So the whole point of this, the really crucial benefit, is that it lets you separate the what from the how. You can say, I need to train a model, and that's separate from how you're going to do it, whether it's with TensorFlow or PyTorch or XGBoost. This gives you just ultimate flexibility. Okay, let's see a real-world example. Let's say your pipeline is completely hard-coded to use TensorFlow. Sound familiar? With the strategy pattern, you'd first define a generic trainer blueprint. Then you can create specific implementations that follow that blueprint. One for TensorFlow, one for PyTorch, another for XGBoost. And the result? It's amazing. You can literally swap out your entire training framework by changing just one line in a config file. No more digging through and rewriting your core code. All right, pattern number 2, the factory pattern. This one sounds a bit industrial, but it's super simple. It's a way to create objects without the main part of your code needing to know all the messy details of how they're created. For MLOps, this is your golden ticket to building really configurable systems. What this means is you can build pipelines that you can change on the fly, at runtime, just by editing an external file like a YAML config. You don't have to touch the code at all. This is how you get those awesome, dynamic, config-driven pipelines. So think about it. Instead of having a bunch of if-else statements in your code to pick a data preprocessor, you just build a preprocessor factory. That factory's only job is to look at a config file and decide which preprocessor to create. And just like that, poof, your pipeline is dynamic. You can change everything just by editing a text file. And that's the key. You're moving the logic out of your code and into a configuration. Okay, last one for our toolkit, the adapter pattern. This is your universal translator, your secret weapon for making all the different MLOps tools play nicely together. It's basically a bridge that connects 2 things that weren't built to talk to each other. It lets you take 2 totally different components with totally different interfaces and make them work together seamlessly. It's like they were made for each other, even though they weren't. This is how you get smooth integration across your whole system. Here's a classic MLOps headache. You have a model trained in Databricks, but its API is totally different from your serving system that's running on Kubernetes. What do? You build an adapter. It wraps around the Databricks model, catches the calls from your serving system, and translates them into a language the model can understand. This is absolutely crucial if you want to build a truly modular MLOps platform where you can mix and match tools. Okay, so to make all these patterns actually work, you need a way to define the rules of engagement, right? We call these contracts or interfaces. It's basically you saying, hey, any component that does this job must have these specific methods. It's how you get everything to speak the same language. And in Python, you've got two main tools for this. First, there's abstract base classes, or ABCs. Think of these as a very formal, strict contract. You have to sign on the dotted line by inheriting from it. Then you have protocols, which are way more chill. They're all about duck typing. They don't care who your parents are, they just care if you can do the job. You know, if it walks like a duck and quacks like a duck, it's a duck. So when do you use which? Well, here's a good rule of thumb. Use ABCs, the strict one, when you are in complete control of all the code in your own application. It makes the relationship super clear. But if you're writing a library that other people might use, or you need to work with code you didn't write, that's where protocols shine. They're flexible and don't force anyone into a rigid structure. Okay, now let's talk about how to take all of this to the next level. There's a modern Python library that has pretty much become essential for serious MLOps work, and it's called Pydantic. What Pydantic does is it takes Python's normal type hints and gives them superpowers. It uses them for automatic data validation and managing your settings. And believe me, this is an absolute game changer for catching bugs and preventing those awful runtime errors that always seem to pop up in the middle of a long pipeline run. And this leads me to one of my favorite Pydantic features, especially for MLOps, something called discriminated unions. It's a ridiculously clean way to implement that factory pattern we just talked about. Here's how it works. You make a Pydantic model for each of your components, like a TensorFlow config. You add one little field to each, like kind, TensorFlow. Then you just bundle them up into a union. And that's it. Pydantic handles the rest. It looks at your data, sees the kind field, and automatically picks the right model. It's magic. It can replace a huge, complicated factory function with just a couple lines of beautiful, easy-to-read code. So when you start using these blueprints, you're really leveling up your game. You're not just writing scripts anymore. You're engineering real, robust, and scalable AI systems. You're building a solid foundation. So the only question left to ask yourself is, which of these blueprints are you going to use first?